paper shows a new decoupling method to simultaneously realize high port isolation and undistorted radiation patterns, namely port and radiation pattern decoupling. MIMO dielectric resonator antennas are deployed for verification. Traditionally, we evaluate the decoupling effect by port isolation. However, isolated antennas may still suffer from distorted radiation patterns. The channel capacity will be deteriorated in the scenarios with a weak multipath effect. To obtain undistorted radiation patterns, a new decoupling method is proposed based on the superposition principle, which is called radiation pattern decoupling (RPD). Let's take H-plane decoupled dielectric resonator antennas case with zero edge-to-edge spacing for example. The field of the working higher-order mode is out of phase inside the two dielectric resonators, but with the same amplitude. Meanwhile, the field induced by the differential posts has the same phase and amplitude. Therefore, the decoupling can be realized based on the superposition of the coupled fields and the induced fields. In this case, the fields inside dielectric resonator antenna 1 and dielectric resonator antenna 2 are superposed constructively and destructively, respectively. Almost no field can be observed inside the dielectric resonator antenna 2, which ensures the port decoupling. The field distribution seems dielectric resonator antenna 1 works under its fundamental mode and dielectric resonator antenna 2 does not exist, which ensures RPD effect. The decoupling performance is then examined. It can be found that this decoupling method can obtain high isolation, low ECC, along with a main beam along the boresight direction, which verifies the design idea. The energy storage distribution is obviously different after decoupling. A new parameter called energy storage proportion (ESP) is thus proposed to evaluate the PD and RPD effects simultaneously, for the first time. It's defined as the proportion of the stored energy of dielectric resonator antenna 1 to the total stored energy in both dielectric resonator antennas. In this case, the ESP increases greatly from 77% to 96%, verifying its effectiveness. A prototype is then designed and fabricated. Conformal strips are used here for low profile. The fabricated prototype is then measured. Over the operating band, its isolation is larger than 20 decibels, the ECC is less than 0.03, and the ESP is larger than 90%. The radiation patterns of one port are given, where stable and symmetrical radiation patterns can be observed. The decoupled dielectric resonator antennas radiate like an isolated dielectric resonator antenna. Similarly, this decoupling method can be applied to E-plane cases. You can find more detailed results in the paper, if you are interested.
Hello, this work presents the analysis of hemispherical dielectric resonator antenna with an imperfect concentric conductor. Figure 1 shows the configuration of the DRA with a dielectric coated imperfect conductor excited by a probe. The Z-directed current is resolved into the theta and R-directed current components. The theta-directed current will excite both the TE to R and TM to R modes. The R-directed current will excite only the TM to R mode. The Green's functions are decomposed into the particular and homogeneous solutions to address the spatial singularity problem and improve computational efficiency. Surface irregularities, presence of an air gap or a layer of paint on the surface can be modeled as an imperfect conductor. The effect of an imperfectly conducting surface has not yet been considered till now in the DRA literature. The potential Green's functions for the theta-directed current for both the magnetic Green's function and the electric Green's function for both the particular and homogeneous solutions are shown in this slide. For the theta-directed current, the unknown constants ANM and DNM of the particular solution can be obtained by applying the boundary conditions at the source point R equal to R prime and are given in equations 3a and 3b. For the theta-directed current, the constants BNM1 to ENM3 of the homogeneous solution can be obtained by applying the impedance boundary condition at R equal to A1 as shown in equations 4a and 4b, and also the continuity of the tangential electric and magnetic fields at the dielectric to air interface at R equal to A2 as shown in equations 5a to 5d. The orthogonality properties of the exponential function and the associated Legendre function can be used thereafter to evaluate the unknowns of the homogeneous Green's function as shown in equation 6. The potential Green's functions for the R-directed current are given in equation 7a and 7b. The corresponding Green's function unknowns H and M to INM3 can be obtained by applying the boundary conditions at the source location R equal to R prime and at the interfaces R equal to A1 and R equal to A2. From the previous Green's function analysis, the characteristic equation of the TE2R mode and the TM2R mode can be obtained and are given in equations 9a and 9b respectively. Solving equations 9a and 9b, the complex resonant frequencies for the TE2R and TM2R modes can be obtained, and thereafter the mode Q factors can be obtained. The variation in the source-free resonant frequency and Q factor of the dominant TE111 mode with the variation in the real part of the normalized surface impedance Zs prime bar for different values of coating permittivity is shown in figure 2. The variation in the source-free resonant frequency and Q factor of the TE111 mode with the variation in the reactive part of the normalized surface impedance for different values of coating permittivity is shown in figure 3. And finally, the input impedance and reflection coefficient variation with frequency for different values of the reactive part of the normalized surface impedance is shown in figure 4.
In the State Key Laboratory of Terahertz and Millimeter Waves, City University of Hong Kong, we engage in a broad spectrum of research from microwave to terahertz frequencies. Terahertz integrated circuits and on-chip antennas are part of our endeavors for a 5-year project supported by the Hong Kong Research Grants Council under the theme-based research scheme.
Dielectric resonator antenna (DRA) is a promising alternative for gain enhancement of on-chip antennas. However, most on-chip DRAs reported use spot-mode metal layer M1 to remove the effect of silicon base and adopt off-chip dielectric resonators, which are similar to antenna-in-package (AIP). In our design, we make use of the inherent silicon substrate and integrate the DR into the chip. The proposed antenna is low profile and it requires no further fabrication. Therefore, it can eliminate the misalignment problem and is suitable for massive production. By carefully designing the dimension of the silicon DR, it can simultaneously excite multi-higher order DR modes and the cavity mode in a wide frequency range. Together, these modes contribute to a wide bandwidth as well as a relatively high gain.
This is a dedicated terahertz measurement setup for S-prime measurement. It mainly consists of 4 parts: the semi-automatic probe station, the microscope, the OML extender, and the vector network analyzer.
For the S parameter, the impedance bandwidth is wider than 50%, with a frequency range starting from 220 GHz to 400 GHz. Measuring below 325 GHz agrees with the simulation after TRL calibration is conducted. On the gain simulation, the 3 dB gain bandwidth is 34.5%, with a peak gain of 7.6 dBi achieved at 305 GHz. Measurement below 325 GHz agrees with the simulation, with stable radiations and low cross-polarization levels.
Our terahertz research positions us for the future 6G and beyond. Thank you for watching.